So next presentation will be done by Alicia, Darren, and Gracia from Group 1. The other Gracia and Alicia.
Okay, so good morning, Pak Dedi, Kak Devita, and friends. So today we are going to present our second milestone presentation of this thermoregulation in an active temperature sensor. So before we start, just a brief overview of our experiment now. We only focus on the thermal regulation part, which means that we want to develop our algorithm feedback control instead of the active temperature sensor and we plan to do that in the next milestone.
Okay, this is some of new equipment that we add. The first one is K-tap thermocouple. So this thermocouple have a positive and negative flag. The positive is made from chromo and the negative flag is made from aluminum. And this is used to measure the temperature of its surrounding. And in this milestone, we use this thermocouple to quickly monitor the nichrome wire so that we can make sure it is regulated or not. The next one is Max 6675. This is used to convert signal from K-tap thermocouple, and it display thermocouple temperature ranging from 1 degree Celsius to 700 degrees Celsius. The next one is 1.5 volt battery. So this will supply volt of 1.5 volts. The next one that we use is S8050. This is a type of transistor that allows a maximum of 700 milliampere to flow across the collector and emitter if it is fully biased. The next one is IRFC44N. This is a type of MOSFET with a high drain current of 49 ampere and low RDS value of 17.5 milliohm, and it is usually used as a switch. The next one is current sensor. So this current sensor uses its conductor to calculate and measure the amount of current applied. This is next. So this is the algorithm that we use, PID, proportional integral derivative. So this consists of three small control, which is proportional, integral, and derivative. The proportional will measure the error between the set temperature and the measure the temperature, and it is determined by the proportional constant Kp. The next one is integral control. This will sum the error that is calculated over a period of time from the previous and the current. And the constant that control it is the integral constant Tk. And the next one is the derivative control. This is the control that is based on the rate of change between the previous and the current output. So the result of these three will be sent back to the PWN to maintain the temperature in the heater. This is the procedure. The first one to do is to attach the K-tap thermocouple to the Max 6675 using the cable of thermocouple. The next one is to connect the Max 6675 to the Arduino using female to male wire. Next is there. Oh my god. The next one is we connect the LCD to the Arduino.
Okay, after that, we put the Arduino, we connected the Arduino to our laptops and opened our Arduino software. And with that, we put in our code. So this is the first part of our code. The top part is mainly for the downloading of the library Max 6675 and Liquid Crystal I2C. And on the bottom, that is the loop for making the circuit continuously display the temperature on the LCD. Next, this is the other part of our code. This is for making the circuit measure the temperature around it. And we actually got this model from online, but we modified it in a way best for our circuit. Okay, next, what we did was try to find the current and voltage that would be best for our circuit. So as our target temperature is 30 degrees, we first applied it to the linear approximation for current as a function of temperature formula above. And from that, we got that we need to get a current of 383.7 milliampere. Okay, after we found the current that we need to find the voltage. And so these are our calculations. From that, we found that we need a voltage of 0.645 volts. Okay, after that, we made a series of 1.5 volt batteries together to make roughly 10 volts. And then with that, we made the following circuit diagram. This is our circuit diagram. And on the next slide, you can see it in real life.
So now we want to attempt to make the PID code using the Arduino so that we hopefully can maintain the temperature. And these were the constant that we use. We actually tried many constant, Kp, Ki, and Kd. Yeah. So this is the code that we try to use for the PID. So basically for this one, the left side is basically to find the change in time. PID error is basically the set temperature, which was set to 30 degrees, and temperature read, which is the temperature read by the thermocouple. And then the PIDP is basically the proportional constant multiplied by the error. The cumulative error is for the integral value later. And basically it sums up all the error from the previous times. The D value or the derivative value is basically the rate of change of error. So PID error minus previous error divided by the time taken multiplied by the proportional constant, the derivative constant. And the PID value is basically just the addition of all, like PIDP, PIDK, and PIDD. And now we want to control the PWM. And PWM range from 0 to 255. And if the PID value total is less than 0, it will make the PWM equals to 0. So it will turn off. So, and if the PID value is more than 255, it will turn it on. And yeah, basically this last two lines is to store the previous error and the time. Now, however, the PID control was not really successful because when we try to heat up, when we try to connect it, the heater just keeps on increasing, even though we already set the temperature to 30 degrees Celsius, and it just heats up to 40 degrees Celsius. And how for this one, you can see like three variables. S is the set temperature, T is the read temperature by the thermocouple, C is the current, using the current sensor, because we use the current sensor to measure the current through the wire. And basically the current sensor shows that the current across the heater decreases as the temperature increases, which is actually what we expected. So yeah, this one you can see later it reaches to 40 degrees Celsius, somewhere there. So if you try to graph the current using the current sensor, it's not a really good result as well. You can see that there are some where the current remains constant even though the temperature increases. And yeah, but if we use a trend line, it still shows that it's decreasing. Now, what we actually expect was that the PWM like turns on and off, right? So at 30 degrees Celsius, we actually expect it to like go up again, so that the temperature remains constant at 30 degrees Celsius. But then because of the PID code, maybe we wrote it wrong. It just keeps on decreasing.
So these are the things that we're going to do next. We're planning to first fix the PID code, but if it still doesn't work, we're gonna plan to revert to using traditional PWM on and off control. Second, we're also going to make the current sensor more sensitive to the current reading. And third, we're going to measure body temperature from the change in current through heater. Thank you for your attention.
Okay, thank you, Group 1. Would like to request Group 3, Dave and Dimas, and Dave only, to ask question.
Okay. I have a question for group 1. Why do you use 10 volt instead of smaller voltage?
Oh, that is because we used the IRFZ44N MOSFET, and that requires 10 volts to turn on. And with that, it can be nicely controlled as a switch. So that is fine.
Yes, and I also want to add, the IRC for N has a really high threshold voltage. That's why we need like a higher voltage to run the circuit. And if possible, maybe we plan, because we found out that the IRC44N is a logic level MOSFET, which means it needs high voltage that cannot be directly run from the Arduino. So we want to try to use the low logic level, non-logic level MOSFET, like that. So we can like directly power it from the Arduino.
It's fine, Dave?
Yes, sir. Thank you.
Okay, Kak Devita, maybe?
Okay, guys. So if the can you please show me the the last slide of your PPT? I'm sorry. No, the last slide.
This one?
No, no. The conclusion maybe.
Oh yeah, this one.
So if the PID code it still cannot working, do you have plan B? Do you have a plan to replace the PID, or you are still evolve keep using PID to control the temperature?
If we don't succeed in the PID code, we'll just use a normal on and off control so that it's easier to implement as well from the PWM.
Okay, so for the graph, current versus temperature. Okay, so how is the graph supposed to be?
So at first, the current decreases, right, until it reaches 30 degrees Celsius. But then if it still keeps on rising, for example, if we put our hand onto the heater temperature will initially increase first, right? Because temperature increases, resistance increases. And so we need to find like a method so that the current is increased. Because current is increased, the power supplied will decrease. So that decreases the temperature to 30 degrees Celsius.
So how you
Okay.
increase the current? Yeah.
Current increase, power decrease. When current increase, power should increase also, right?
No, current decrease and then power decreases.
Current decrease, power decrease.
Mm-hmm.
So, what is it related with the body temperature? How is it related with the hand temperature that you touch?
Yeah, for example, if we put our hand onto it, it will increase in temperature first, right? Because it increases in temperature first, the resistance will increase.
Okay.
Because resistance increase, the current will decrease, right?
Why?
Because they are inversely proportional, right? V equals to IR.
The current increase, resistance increase because the power remain the same.
And then current decreases, right?
Current decrease. Okay.
And now to feedback, the current has to be increased.
Yeah. Okay.
And the change in current can be used to measure the body temperature.
Yeah.
Hopefully, we can
Good.
accomplish that.
Okay. Now I understand, because during your presentation I could not get no part of your presentation clearly explained that part. Yeah.
Yeah.
I don't know who did the presentation on that part, because you are there. But now when you answer the technical question, now I got what you want. So this is a bit different. Yeah. So you are using current sensor. Nikki's group using voltage sensing, voltage detection, voltage change detection. In your case, you want to detect the current
Yes.
change. Okay. Okay, Kak Devita, any more question?
Yeah, that's all from me today. Thank you.
Yeah. Okay, just from me, I think please make it more easily to understand. Yeah, your presentation. I think the other groups like make it more easily to understand also. Yeah, the PCR of course maybe understand, but this project is not that easy to understand. Sometimes you need to explain the logic first, yeah. Then the PID. PID is only the one of the method, right, to control the current. But the whole system mechanism you need to explain first to the audience so that we can understand. And secondly, yeah, 12, 12 large 1.5 volt batteries. Is it wise wise choice? Why don't you use, for example, one single 9-volt box battery plus one single additional 1.5 volt, and it will 10.5 volt. You never know.
Because
Yeah.
we read for the 9-volt battery, the milliamp hour is lower, right? It's lower. It's really low. So we're afraid that
It
we might
depends.
damage the battery.
It depends, depending on your choice of the battery, and also depends on the power that your heater draw, yeah, from the battery. You need to calculate a little bit so that then you can estimate how much time you have with a single battery configuration. Maybe or presumably it's better, for example, to use the chargeable battery, for example. My point is to make your setup more compact, yeah. And also you can use smaller voltage battery, but then you use inverter, power inverter. Correct me if I'm wrong. To increase the voltage, or voltage regulator. Yeah, a voltage regulator that can also increase and make the voltage steady at 10 volt. Maybe something like that. I don't know. There are many other ways besides having to put large 12 large batteries. That's it. Okay. This is not compulsory, but I think in terms of neatness, yeah, the way that, because we want to use this sensing, for example, as a portable device. If the batteries themselves are very large, it is not practical. Okay, just as a suggestion for your group, if you want to take it, very good. If not, yeah, okay, it's your choice, your group choice. Okay, group one. Thank you very much. Then I would like to call next group two, Catherine and Elisa, to present their second milestone. Yes, you may start, Catherine, Elisa.
Yeah, wait. Okay.
What happened?
My internet is quite slow, so it's still loading to present.
Maybe Catherine can be the one that share the screen rather than Lisa.
Oh no. Okay.
Good afternoon, Sir Dedi and Kak Devita. Today, me and Alicia will explain about thermal regulation in a PCR chamber.
So on the previous milestone, we already made something similar to this, but on this second milestone, we decided to upgrade it after serial discussion. So now we have so some part of it still the same as the first milestone, such as the Arduino, the breadboard, and the LCD. What difference is we've added relay for the sensor, another relay for the Peltier plate that will act as a heater, and then a petri dish that will basically hold the PCR chamber. We only presented a drawing because most of the things that we ordered haven't arrived yet, so we haven't got the chance to make the circuit yet. So this is the improved diagram flow based on the new equipment that we've chosen. So after the system is started, the initializing process will start, and then the Arduino will basically tell the sensor to turn on and the heater to turn on. Then when the temperature already reached 95 degrees Celsius, the heater will be turning on and off again on a repetitive motion for 10 seconds. And then after that, it will turn off. After with the heater off, the temperature will reach 65 degrees Celsius, after which the heater will turn on and off again in that repetitive motion for 10 seconds. And then after the 10 seconds has passed, the heater will stay on until the temperature of 72 degrees Celsius is reached, which after that, the heater will be turning on and off again for 10 seconds and then going back to this part. So yeah, this is the list of equipment. So we have Arduino Uno R3, we have a DS18B20. This is a temperature sensor. We chose this sensor due to many of its advantages. Also, we have a pelter plate. On this instance, we use pelter plate as a heater and not a cooler. We also have petri dish. We use petri dish to hold the PCR chamber as what we've learned. The PCR chamber is quite thin and it is shaped like a square. So we were thinking about uh, what that could hold the PCR chamber, and then we chose petri dish because it is relatively heat and cold resistance. We also use a relay that basically allows the circuit to be switched by electrical equipment and also to transform the AC circuit to DC, the AC, to turn an AC to DC. And LCD, we also use LCD to display the temperature. This is the visualization of the equipment. This is the DS18B20, the Peltier plate, and the relay, the LCD.
So, the system that we want to used in this project is the PID temperature control system. What is this? It's a loop control feature found on most process control to improve the accuracy of the process. And the purpose is to maintain the process temperature at the set point for desired period of time and avoiding any separate change from lack of pressure or disturbance. And how it works, theoretically, PID control works using a formula to calculate the difference between the desired temperature set point and the current process temperature. Then it will predict how much power to use in subsequent process cycles to ensure the process temperature remain as close to the set point as possible. So practically, paired temperature control differ from on or off temperature controllers where 100% power is applied until the set point is reached, at which point the power is cut to 0% until the process temperature again falls below the set point. So this is the formula for the PID controller and the elements, and its element is PID. P is for proportional gain, I for integral gain, and the D is for derivative. In the formula, PID is denoted as Kp, Ki, and Kd. So why we use PID temperature control system? Because it's effective at dealing with the process disturbance. So if the PID controller is turned on properly, it will compensate for the disturbance and bring the process temperature back to the set point. Okay.
Okay, finish.
Yes, sir, because the material haven't come
Right,
yet.
yes.
Why? Elisa is near Batam. Batam is the center of microelectronics industry in Indonesia. Catherine, you are in Surabaya, right?
Surabaya. Yes,
There is
sir.
Pasar Genteng. You just go to Genteng. You can purchase all the electronics component there. What happened to you? Both of you?
I buy
There
it
is
online.
a store here that sells that, but not everything, sir. I already checked, but not everything is available. So yeah, still waiting on certain equipment to come.
Batam, you can just go to the factory, purchase which component, like IC. It's everything is there in Batam. Like Surabaya also, you have Genteng. Go there. No need to go.
I haven't from home since pandemic.
Yeah. Otherwise, also there is also online store which is located in Surabaya, which you can purchase.
In Batam, there back then there was a lot of stores that sells this kind of stuff, but now it is very hard to find store that is still open.
Yeah, but you can call them and I want to purchase this component. I transfer to them and then make them send it to you to your address. It's just like that. Okay.
Don't have connection to the company, sir.
No, there should be any website, right, that you can contact. Yeah. So my point is, well, the other groups already started their experiment to see that your group hasn't done anything yet at all at this second milestone is very disappointing because based on the experiment is that we can give you more feedback, what to improve. Yeah. So because until the final presentation will be you only have 2 or 3 weeks, right? The other one that this project, Jesse and Hanif already have some presentation, some result. Dave, Dimas already have some result, even though with their rough setup, but at least they have done something. Yeah. What happened? So, okay, Nikki, Michelle, please ask short question to Catherine, Elisa.
You guys from group 2, right?
Yes.
Okay.
Betul.
So why do you use what was it again? DS blah blah blah.
18P20.
Yes. Why did you use that as
This
the
one.
sensor?
Yes, first because it's waterproof with temperature range from minus 55 to 125 degree, and the second reason is because it's digital temperature sensor, so we don't need to calibrate it, so it's easy to use
Okay.
than thermistor.
Okay. Thank you.
Okay.
My question is, in your equipment, I cannot see cooler, unlike in the other groups. Why do you not use cooler?
Yeah, good
Oh
question.
yeah, for we were planning to use Peltier plate as a heater, right? So previously we already discussed if we can stack up a Peltier plate that will act as a heater and a cooler, but then we found out that it is not possible, and so we decided that to cool the system down, we will use no cooler, just the surrounding room temperature. If that didn't work, we were planning to use an external fan to cool down the temperature. If uh, after that, if that didn't work again, we will install a small fan near the PCR chamber.
Yeah, you mentioned if that not didn't work, if that didn't work, but you haven't tried
Yes.
anything at all.
Yes, sir.
Better
No
to
equipment
have
yet.
better to plan the better to plan correct from the beginning. Peltier is usually used as cooler. Heater is usually we use different microm wire like the other groups or other heaters.
Yes, sir.
Okay, Kak Devita, maybe one question. Thank you, Michelle and Nikki.
Yeah, well, actually, I have no question. Just want to give you a suggestion, guys. Even I mean, although your component isn't coming yet, is your component is still shipping process, but please try to create the proper circuit in proper software, yeah, so that you
Yes.
can understand the pin out, and how to connect the
Oh ya.
each pin, ya.
Ya.
Jadi kalau kayak gini kan pin outnya
Ya.
gimana?
Ya,
you
it's
will
Sama
really hot.
sekali, belum
Yeah.
nyoba sama sekali. Tangannya belum nyentuh komponen sama sekali.
Yeah.
Jadi komponen from SU already arrived.
Already, sir.
Already, sir.
You can already try Arduino thing, something like that. Connecting
Yeah.
the Arduinos. Now no result at all. Alamak.
Yeah. Okay, guys. At least from the circuit, from the maybe Eagle, and from another software, you will not so apa namanya asing, tidak terlalu asing sama komponen-komponen yang akan kamu pakai. Udah, gitu aja. Thank you.
Yeah. Okay, thank you, Kak Devita.
Thank
Okay.
you, Kak.
No question. I've said too much. I can say more actually, but I don't. If you see me angry, get this even more disheartened. Okay, next group. Osama and Martin.
Thank you.
Sama?
Okay.
Are you there? Okay.
Yes, I'm here. So good afternoon, everyone. Today, Martin and I are going to present the new updates of our project. So first of all, the first thing that we made, next slide. The first thing that we applied in the project is the pulse weight modulation, PWM. So let's see the video first.
Okay.
Okay. So as what we can see here, PWM allows us to control certain analog variables, which are in our case the voltage and the current. And as it can be seen here in the video, it's applied correctly. The components here in the video are the breadboard on the right, the Arduino above the MOSFET, and then the MOSFET here. So next slide. So as it can be seen here, the MOSFET can be noticed. It's connected to the Arduino PWM signals, which are -9, not minus. I don't know actually the signal. What does that mean? 9, 5, 3, 2, and I think 1. And then this is to the PWM plug and to the ground, of course. And the supply plug can be connected to the Arduino itself or to outside supplier. And as it can be seen here, and the output may be load the load here to the load current. And the range here is for PWM signal from 0 to 255. So let's say example that our voltage is 5 volt, and the PWM signal is 255. So the V output will be 5 volt. But let's say if it's the half, 125, the output would be the half of the input voltage.
So okay, as you can see, this part is the supply, and the PWM signal controls the output current and or voltage. So now, how the Arduino can tell what current is flowing into the load and what voltage is across the load? So we need a feedback. The first one, to calculate the current, we can use a current sensor. But if we choose to calculate the voltage, we can use a voltage divider and calculate the voltage to the analog input. So in this circuit, we use a current sensor. So from the MOSFET, it creates a PWM signal from here, the output, and it goes, I think we cannot see the heater component here, but there's a heater component here. It's small. And I think this also brings a problem. The heater is too small. The resistor of the heater is too small. So the calculation is not accurate. So, and then we can observe the current using the current sensor here and fit it back to the Arduino. So here we can see, wait, I cannot see the top part. What is this? Oh, this is maintaining the current. So as we can see here, there is a current sensor. So if the current sensor is higher than the current that we want, then the PWM will be -1 and the voltage decrease and the current will decrease. Wait. If the current is high, yeah, that's right. The voltage is decreased. So we can maintain the current here. And then how we measure the temperature? So we measure the temperature by the PWM signal. As we know before that PWM range from 0 to 255, if I'm not mistaken. So let's say the initial PWM to give a certain amount of current and a certain amount of voltage is, let's say, 120. So if the final PWM signal is more than 125, then we can get the PWM change. Then with this change, we can calculate the temperature. Okay, but unfortunately, it's a theory. Now we cannot measure the current sensor because I have a problem in the current sensor. So I think we should fix the current sensor first. If we can measure the current, then we can apply this algorithm to measure the temperature. Thank you, sir.
That's all, finished?
Yes, because the current sensor is not working. I don't know why.
So you mean you haven't figured out what current sensor circuit should look
No,
like?
I have. We use this one, the sensor. ECS 712.
Yeah, how does it schematically shown? You are showing the component, but schematically, how is it?
So
How does it measure current?
so there is 2 pin here. It goes to the what let me say. So the current is flowing from this yellow wire to the current sensor and going out from this green wire back to the heater component.
Yeah,
And
I mean, next time you have to show the schematic
yes,
of that component, yeah, within the system itself, not just current sensor or just the picture of the component, but what is the schematic? We want to know, we want to learn how you measure current. Okay, Jesse, Hanif, ask questions.
Hello, can you hear me?
Yes.
Okay. You said that there was a problem with the current sensor, right? And voltage measurement. And how do you fix the problem for that, Tin and Osama?
So first thing, I will change the heater because the heater's component resistance is only 0 point something. It's very small. That caused the current just flowing through it like it was nothing, I think.
How I didn't quite get it. Sorry. How do you fix it again?
So the heater's component, the resistance of the heater component is very small. So I think that makes the problem when calculating using the current sensor.
The resistance is too small, so you need to use a bigger one.
Yeah.
Oh, okay. Okay, I get it, sir. Thank you, Tin.
I also want to ask you maybe just how do you prove like that PWM is applied, PWM is applied?
Osama?
What?
How how do you prove that PWM is applied?
Oh.
So okay, if you see the video here, the white light is turning on and off, on and off, on and off. Maybe you can play it again.
It just showing like it turns on all the time.
So it's no, it's not. It's in
Oh,
the
is
video.
it green?
Yeah.
Look, which one? Which lamp? Oh,
the white one.
Huh? The white on the right.
Yeah.
It seems
Actually, this one is the MOSFET itself.
Too bright. Too bright that we cannot see the blinking. Oh, okay.
Maybe because of the
Yeah, a little bit.
Yeah.
Little bit.
So it's turning off. I know. On and off.
You should make longer recording so that you can see it later.
Yeah.
Okay, Hanif, answer your question or not? Not yet.
And I also want to ask like how like does it how does it like maybe turn on and off so fast maybe?
This is because of the programming of the PWM, because PWM technique make it 50% of the wave is on and 50% is off. So it depends on the waves.
So you can see the pin here. So pin number 3, 5, 6, 9, 10, and 11 have the symbol. It's negative but wavy. So that are the pin that can make a PWM signal.
Okay, Kak Devita, maybe one question.
Okay, guys. Have you guys already figured out the algorithm? You didn't put it here.
The algorithm. Yeah.
The algorithm for which one?
Yeah, for controlling the heater.
We haven't made that because when we want to measure the current value is wrong and it's not stable. Let's say it's 0.1 and then 0.7 and then 0.1 again, 0.7 again, something like that.
Yeah. So
Yeah, because you can put it in. You can put it here, yeah, in a flowchart, or maybe just take a screenshot from the IDE.
I have them.
Oh, Oh, really?
One is for measuring the current and voltage. So we use serial print with, we don't use the LCD, we use serial print. So we can see it
Okay.
in the monitor.
But
And then,
what you haven't put is the algorithm, how much voltage increase
yes, that,
you will
yes.
you will do when the current is decreasing at certain number. This algorithm, whether you are using on off the ID, how much the level. You understand? So that is not yet there, not yet here in your explanation. You just mentioned current decrease, voltage increase, current increase,
Yes.
voltage decrease. But how much decrease how much current increase will cause will cause how much voltage increase. This thing is not yet clearly explained or not yet done.
Hmm.
Has it been done? Not yet.
Not yet, because
Uh,
I actually want to find the current first. Then with this current sensor, I can make that algorithm. So
Yeah, of course, current sensor. There are two of you, so one can find the current, the other one can already think about the control algorithm. Yeah, so share the task. Okay,
okay, sir.
because you have
That's all.
not much time to revise again. Okay, thank you, group 5. Group 5. Martin and Osama. Yeah, some details are missing in the presentation. I hope you can complete all the details. So that is all for today. All the 6 group, thank you for your presentation. I will try that your final presentation will be at the second week of the final exam week. So it means that it will be another 3 weeks from now. Yeah, should be enough. Yeah, so don't make excuses again. Components hasn't arrived. This like this.
Yes, sir.
What the kind of excuse is that? Always Elisa is doing at the last time. Uh, Sending to me signature during the last time. Okay, Elisa.
Yes, sir.
So please do it properly because no written final exam anymore. Okay, so this presentation, your demonstration, if it works, you will get good mark as well. If it doesn't work, yeah, depending on how you find the explanation. And this will also form the mark for your lab subject. Okay, as the final exam of your electrical lab. Any questions so far?
Sir,
Yes.
I want to re-ask about my